Yeah, yes, it's nice to be here. I used to study here 15 years ago, 12 years ago. So it's nice to be. They did not have this building back then. It's nice to be back. Okay, so today I'm going to tell you about interactive proof systems. Okay, so but before we get there, let's start with something much simpler. So let's start with okay. Take this statement. Okay, so we all know this. We know this is true across like all sorts of fields and everything, and even some rings and all. But how do we prove this? How do we prove a statement like this? What is the proof of this statement? Imagine you want to prove this over real numbers. Let's say. How do you prove this is true? Can somebody say it louder? So to expand this, so what I would do is I would say this is equal to, let me write it this way. I would say the left hand side is equal to just, what it means is a plus b times a plus b, right? This is what the square operation means. And then we know that the multiplication distributes over addition, right? So this means that you can write this as, you can multiply these two things, a squared, and then you can multiply these two, and then you get, and then you multiply these two, and then you get these two. Right, so you can expand this using the distributivity properties of multiplication into this, and then you know that multiplication is commutative, so you can put these two together and you get this to be, and this is equal to the right hand side, right? And at each point we know like what property we used. Here we just use the definition of the squaring notation or the squaring operation. Here we use the distributivity. I'm not going to write this out fully, but here is distributivity, and here we use the commutativity property. Right? And this is how we typically do proofs in mathematics. Right? When you want to prove something, something like this, you say, okay, I start with this, then I apply some very simple rules over and over. Right, here I use this one simple rule, I use different rule, I use a different rule, and so I can make this sequence of statements such that if you can verify every statement in this sequence, like if you can verify every equality, if you can verify that this equality is correct, this equality is correct, this is correct, and so on. If you verify the entire thing, then you would have verified the entire proof. Right? This is what we typically mean when we say proof in mathematics. But in our day-to-day life, right, in other contexts other than mathematics and trying to do things rigorously, we also have other weaker notions of proof, right? And there are many kinds of these. For example, if you want proof that some event happened, some big event happened, and if it's reported in the news, you tend to believe it happened, right? Maybe to a different degree today than a few years ago, but it has some, it convinces you to some extent that things have happened, right? So in some vague sense, this news broadcast talking about something is a kind of proof that something has happened, because you watch this and you believe something has happened. It's in the same way that you can read this proof and you believe that some statement is true, right? A different kind of proof, which is maybe simpler and more believable sometimes, is the following example. So let's say that so I tell you, suppose imagine this hypothetical scenario, okay, where you don't have the sense of taste or smell. Okay, all you can do is you can see, right? And now I come and I tell you there are these two drinks, let's say like coffee and tea, which they don't actually look the same, but let's say they look the same. So I come and tell you these are actually two different drinks, right? But you don't believe this, because to you they both look like these brown hot liquids that have the same consistency. Right? Now, how can I convince you somehow that they are actually different? How would I be able to convince you? Like you cannot taste anything, you cannot smell anything. Yeah. What do you mean? Can you give more details?
I can take both of them. There are two different cups of tea, right? So I'll randomly pour one of them into a different cup. I'll give it to you, and you have to tell if it's the first one or the second.
Yeah, exactly, right? This is a very simple sort of blind testing that you can do, where you take the two things and then you remove the labels, right? Maybe these two things come in different kinds of cups, but you take a different neutral thing that is the same in both cases, and you put it into that new cup and you give it to me, and I have to tell you what it is, right? And now if they are in fact different, and if I can in fact tell the difference, then I will always be able to say what you gave me. So you can just check, am I giving you the same response? Am I answering correctly every time you ask me what is this, right? On the other hand, if they are actually the same, if I am lying to you, then I would make mistakes, right? Like I would not know what you put into it. So it probability half, maybe I can get lucky and guess something, but every time you do this with some probability, with probability half or something, I will get it wrong. I won't be able to respond correctly. And then you can repeat this experiment many times. Like if you do it 100 times, for example, the probability that I will get lucky every time is very small, right? And so this would give you some reason to believe that these two things are in fact different. Like even though you cannot tell the difference, the fact that I am able to do something is convincing you that they are actually different, right? So this is again an instance of a process that is able to convince you of the truth of some statement, right? It's not as strong as a mathematical proof. It's not as rigorous as a mathematical proof because it has this small chance that I can get lucky every time you try it, right? Whereas with a mathematical proof, there is no chance it is wrong. Like if I wrote these things, if all the axioms I started with are true, if all of these properties are true, then this is definitely true, right? But in this process, there is some possibility of error, but still it is something. Like it is convincing you of some statement. Like even if you did not believe it earlier, you have some reason to believe it now, right? And this kind of a proof where I prove this statement something to you using this kind of interaction, because this is another way in which this is different from a mathematical proof, right? In the case of a mathematical proof, I can just write the whole proof out on a paper and give it to you, and you can verify the entire proof. But this process that we just described is inherently interactive, right? You can imagine there are other ways I could prove that the two things are different, right? Like maybe I can do some kind of spectrometry and I can show you that the molecular composition of the two things are different, and that I can actually write down on some piece of paper and give it to you, and you can verify it on your own, right? So there are ways to prove these statements without needing interaction, but adding this interaction makes things much more efficient, right? Because this process that we just did is much more efficient than me using some kind of special chemistry equipment to prove that coffee and tea are different drinks, right? And this is what we are going to talk about today. These kinds of proofs where we prove things in a manner that is perhaps less rigorous than what you typically do with typical mathematical proofs, but still meaningful in certain contexts, right? And we are going to try to think about how you can argue about these things formally, what properties these kinds of proofs have, and what they can do, what their power is, and how they can be used for various things. Okay, but before we go there, before we talk about how to formalize these things and all, let us see another example of such a proof system, of a very similar kind of statement that I want to prove, but that's a bit more mathematical, so that I can talk about it more rigorously, right? And the specific kinds of statements I want to prove now are about what is called graph isomorphism. So how many of you have heard of graph isomorphism before? Okay, about 60% of you. And how many of you have heard of graphs before? Okay, so pretty much all of us know about graphs, right? Great. So the graph isomorphism problem is the following, all right? I'm going to give you two graphs. Let's say, for example, like this graph, that it's going to be, let's say I give you like two graphs on 4 vertices, okay? And I'm going to number them 3, 4. This is the first graph, and it's going to look like, let's say I have this edge, I have this edge, I have this edge, I have this edge. Okay, this is one of the graphs, and I give you another graph, which again 1, 2, 3, 4. So I give you two graphs like this, okay, on the same number of vertices, and they are numbered like this. The vertices are numbered from 1 to, let's say there are n vertices. Here there are 4, so I number them from 1 to n. And the question I ask you is there some way of renaming the vertices of one graph so that it becomes the other graph? That's the question. Like, does there exist such a relabeling or not? Right. So in this case, so if that happens, the graphs are said to be isomorphic. So what about these two graphs? Are they isomorphic? So 2 and 4, if I exactly. So in this case, if I just let me use a different color for this. So in this case, if I just change the labels for these two, if I made these 4 and made this 2, then you see it's exactly the same graph, right? So these two graphs are isomorphic. And this problem, of course, it's very easy to do it for graphs with a few vertices, right? But till today, we don't have a polynomial time algorithm that can solve this problem. If I give you two graphs on n vertices, we don't have an algorithm that runs in polynomial in n time, and for any pair of graphs on n vertices can tell whether they are isomorphic or not, right? And it was in fact only very recently, about only a few years ago, that people found something like an n to the log n time algorithm that can solve this problem. This was a really big deal. This was after decades of work on this problem, but we do not have a polynomial time algorithm for this problem, right? But the question that we are going to deal with today is not about how to solve this problem, but about how to prove statements of the form these two graphs are isomorphic or these two graphs are not isomorphic, right? So how do we do that? Let's say I wanted to prove to you that there are two graphs. Okay, there are two graphs that both of us know, and I want to prove to you that they are isomorphic. Or let's say you want to prove to me, right? Like for example, that in this case you know they are isomorphic. Let's say I don't know, right? So how would you prove to me that they are isomorphic? Yeah, you just did, right? You proved to me that these two graphs are isomorphic. You told me how I can relabel them so that they look like the same graph. So all I had to do is you told me, okay, if there's 1 here, what should I change it to? In this case, you keep it as a 1. In this 2, you told me I change it to a 4. This 4, I change it to a 2. This 3, I keep it as 3. I did that, and then now I can check that the two graphs are the same. And that's very easy. That you can do in like linear time in the number of edges or whatever, or quadratic time in n. Right? So proving that two graphs are isomorphic is very easy because you can just give me the relabeling itself. But how do you prove that two graphs are not isomorphic? So this is a natural approach to take, but it can be a bit difficult to implement. Like let me show you an example. Let's take an example of two graphs that are not isomorphic, and this I think is a good pair of graphs that might. Okay, it's hard for me to show that anything you can think of doesn't work, but some of these things, the fact that some of these things don't work can be illustrated by some graphs like this. Like imagine I have these two graphs, okay? So one of them is a cycle with 6 vertices, another is like you have the same 6 vertices, but it's like 2 different cycles of 3. Right? Now, how would you prove, for example, here that these two graphs are not isomorphic? So this is a very good thing to try. A degree sequence is a very good thing to try. So let me explain just in case, just to have us on the same page, right? The degree of a vertex is the number of edges adjacent to the vertex. A degree sequence is just you take all the vertices and you look at take the list of all of the degrees and put them together. That's the degree sequence, right? And this is actually what I want to illustrate. These are very natural things to try, and these are in fact things you think about when you are trying to design algorithms for graph isomorphism. When you think about these things, okay, clearly if the set of degrees of the graph, if the degree sequence of two graphs are not the same, then they are not isomorphic. Right? So that's one way to do it. If it happens that your graphs are not isomorphic, then you can't do it that way. If it happens that the degree sequences are not equal, then that would be one proof, right? So these proofs are sound in the sense that if the degree sequences are in fact different, then the graphs are not isomorphic. But the difficulty with these proofs often is that they're not complete, meaning any proof system you can think of, like whether a mathematical proof or whether it's a news or whatever, needs to have two important properties. Okay, so one is the more important property I would say is that it has to be sound. So if the proof works, if you are able to look at the proof and verify the proof, then the statement that it is proving has to be true. That's a property you want for any kind of proof system. For any method of proving things, it has to have this property. And this property is called soundness. Okay, so let me write it down over here. We will define these things more formally later, but so this property of a proof system is called soundness, and I will write it as only true statements can be proven. Like if I'm able to prove something to you, if I am able to give you a proof, and whatever verification procedure you have tells you that the proof is correct, then the statement that the proof is proving has to be true, right? And the other property you want, and so this approach, the degree sequence approach to proving that graphs are not isomorphic, has this property, because if you find that the two graphs that you have two different degree sequences, and you give me these two degree sequences, and I verify that the graphs do have these respective degree sequences and they are different, then there's no way the graphs are isomorphic, right? So this approach of proving that graphs are not isomorphic is sound, meaning that if the proof proves something, then the statement is true, right? But the issue with this approach is it's not complete. This is the other property you want from any kind of approach to proving things, which is that you would like to be able to prove ideally all statements that are true. Right? You want any statement that is true, you would like to have a proof. Any statement that is true and sort of expressible in the language you are working with, you want to be able to prove. And that's also a desirable property of a proof system, right? And that property is called completeness. So these are two properties you would like from any reasonable proof system, right? Of these, I would say soundness is the more important property, but you would also ideally like to have both of these, right? And I'm not going to go too deeply into these properties in the more general sense, because but if you are interested, you should look up. Maybe some of you have heard of this. You should look up this thing called the incompleteness theorem, Gödel's incompleteness theorem, which sort of in a broader sense it says that you cannot have proof systems that have both these properties that are non-trivial. Right? But in our limited context, it's going to be possible. We are only going to look at proofs of certain kinds of statements and certain kinds of proofs. So in our context, it's going to be possible, especially because we are going to be dealing with these interactive proofs which can have some error. Right? We are only going to ask for these to be approximately true. So we don't have to worry about that now. But if you are interested, I would, and it's some really fascinating stuff actually. So I'll just put it over here and just look it up later if you haven't heard of it before. It's called Gödel's incompleteness theorem. Okay, but it's not really relevant to us for the moment. But this is what I want to say. Like these two properties, you would like your proof system to have. Right, and the reason I'm saying that the degree sequence approach to proving these things is not complete is because it cannot distinguish between these two graphs. Right, because these two graphs, every vertex has degree 2. Right, so they have the same degree sequence. Right, so these, but they're clearly not isomorphic. But but this approach is not able to prove it. Right. Of course, there are other approaches you can use to prove it. For example, if you count the number of triangles in this graph, number of cycles of length 3, they are different over here, right? But in general, we do not know a way that we do not know an approach to constructing such a proof that you can just constructing a non-interactive proof like this, like the one you gave me here, right? In this case, you are able to just write down this one thing on a piece of paper, and I can verify it later, right? But we do not know an approach to proving non-isomorphism in that manner. Like I do not know how to give you for any two graphs that are not isomorphic. I do not know how to give you like a reason, give you a proof that it's not isomorphic that you can just verify on your own, right? And if you are able to discover such a proof, I think it'll be quite interesting. It'll be something of a breakthrough, but we don't know how to do it, right? But we do know how to prove that two graphs are not isomorphic with an interactive proof. And in fact, you already know how to do it. So how would you do it?
Both of these can be considered as different cups of tea. I mean, the claim is that they are both different cups of tea, and then the verifier can randomly select one, take a relabeling of it, send and ask. I mean, for both of them, and then ask if they are the same or not.
Yeah. So this is basically the idea. So let me repeat this, right? So what we are going to do is we are going to take the same approach we did to the coffee and tea example we did in the beginning. But there, what did we do? We had these two things, and the person whom I will refer to as the prover from now on. Okay, so where the verifier is trying to verify something, is trying to verify the statement that this person called the prover is making to them. Okay, so the prover is saying coffee and tea are different. The verifier says, okay, prove it to me, and here is how you are going to prove it to me. I'm going to pour one of these two things into this third cup. You don't know which one. I'm going to give it to you. You tell me which one I poured, and I know which one I poured, so I can check that you're correct. Right? We are going to do a very similar thing over here. We are going to say, okay, I have these two graphs. They are either the same graph in some sense, or they are not. And the sense in which they are the same graph is that there is a relabeling of the vertices that makes one exactly the same as the other. Right? So I have these two graphs. So what I will do is I will remove all sorts of extraneous identifying information from this graph, because that's what we did with the coffee and the tea, right? They initially came in their own separate cups. Maybe you got the coffee in a tumbler and the tea in a cup or something. But we removed that information. We removed the information that would have otherwise identified the drink to the prover, right? The information that is not actually relevant to the property you're testing for. So in this case, that information is the specific labels of these graphs, right? So what I'm going to do is I'm going to erase this information somehow, and then I'm going to give the graph to the prover, and I will pick one of these two and give it to the prover, and I will ask them, okay, which one did I give you? Right? And how do I do that? In this case, the only information is the labels, right? So what I will do is I will just randomly change the labels. Imagine what you want to do is erase the labels. So instead, what I will do, and this is an equivalent thing to do, is I will just label these things randomly. Okay? Instead of 1, 2, 3, 4, I will pick for each of these. I'll pick some random thing that is without repetitions, of course. So maybe I'll change this to a 4. I'll change this to a 2, a 3, and 1. So I will pick like a random permutation of the labels. A random relabeling is how I will refer to it. So I will take this graph. I will randomly pick a labeling for the vertices. Like I will forget the initial labeling, and I will pick a new labeling for the vertices at random. And then I will send this graph to the prover. So I will do it with either this one or this one, and the prover has to tell me which one I give. Right? And here you can clearly see if the graphs are in fact isomorphic, then these will look the same to the prover, right? Because I'm going to remove all of the labels and then put in a random labeling, and here I'm going to do the same thing. But if I remove the labels, they are the same. So the distribution of graphs I get from this and the graphs I get from this are going to be the same. So the prover has no way of telling which I started with. So maybe it will get lucky and guess correctly with probability half. But if I just repeat it enough times, the probability it succeeds every time is going to be very low. Right? Whereas if I do the same thing with this graph, the prover is going to be able to tell, right? Because whenever I take this graph, I erase all the labels, put in random labels, give it to the prover. It's always going to see that this is a graph that has one cycle of length 6, and this is a graph that has these 2 cycles of length 3. So it doesn't matter how I label these two; they will never look the same. Right? And this is the proof system. Any questions about this so far? Yes. So so what is the verification in this case? So let us write this down more carefully, and so that we can think about this more clearly. So I'm going to write down the proof system, okay? And all of my proof systems are always going to be between these two parties, one of whom I will refer to as the prover, and the other I will refer to as the verifier. Okay? And in this context, we are only going to be talking about these graphs, right, for the moment. So you can think of this as this is going to be an interactive protocol. And the input to the protocol, which both the prover and the verifier get, is going to be this pair of graphs. So there's going to be some G0 and G1. I'm writing it in the middle because I mean that this is given both to the prover and the verifier. Okay, so they both have this, and now the prover is trying to prove to the verifier that the graphs are different, that they are not isomorphic. Right. So what was the protocol we just discussed? Well, what the verifier does is initially it picks one of these two at random, and I'm going to represent that by a random bit, So I'm going to pick a bit at random from bit B at random from 0 and 1. Then I'm going to pick a random relabeling, which is what I'm going to erase the labels and label them afresh at random, right? And I'm going to just I'm not going to fully explain how to do that. You have to be it's not immediate how to do it correctly, because you have to make sure it is random and that it is a permutation, but it's not that hard to do. So imagine you can do it, right? So I pick a random relabeling of and this is basically just a permutation of the numbers between 1 and n essentially. So you just have to pick a random permutation of numbers between 1 and n. You can do that in polynomial time. You can think about how to do it efficiently actually. If you want to get the most efficient algorithm for this, there are some clever algorithms that do it. But it's not that hard to do. So imagine you can do this. And then what the verifier is going to do is it is going to apply this relabeling to the graph indicated by this B, right? So it is going to say I'm going to compute a graph H that is a relabeling of the graph GB using the relabeling R that I picked over here. Right? I'm going to take this and then I'm going to send that. The verifier is going to send this H to the prover. Right? And now what is the prover's algorithm? What should I write here? But how does it compute the B prime? I see. Is it okay? But the thing is there is no permutation. The prover is claiming that there is no permutation pi that can turn G0 to G1. Yeah, it's trying to prove that there is no isomorphism. Say this again. So if you just have the two graphs, then no. But if you have but if you have the relabeling, then yes. But if you have just the two graphs, then we don't know an algorithm. But here's one thing. Here's where I want to bring this in. So the way I want to model my system is I want my verification to happen in polynomial time, but I'm going to allow my prover to run in whatever time it wants. I'm not going to place a bound on the power of the prover. Yes, so that's what the prover is going to do, right? And the reason I want to model it this way is one, it makes sense from the perspective of you can take a more philosophical perspective of what is a proof, right? Like what is a proof? It's something that convinces you of something. If there exists a system where you have, even if the prover is inefficient, if you have this protocol, then the proof will convince you that the statement is true. So from that point of view, it's acceptable for the prover to be inefficient. But actually, perhaps more importantly and more relevant to what we'll be doing later, it's in systems where we want to use proofs like this. I'll say a little bit more about this later in the afternoon maybe. It sort of makes sense to have the prover be less efficient than the verifier. Because typically the set of cases where you will want to use proof systems like this is when you have a weaker verifier that's trying to get something done from the prover. Like imagine, for example, that you have some computation you want to perform, and this is an application that people are quite interested in these days for these kinds of proofs. Imagine you have some program you want to run. Okay, so you have written a program, you have some input for the program, and you want to run it, but your computer does not have enough resources, right? Because you don't have enough RAM and don't have enough processing power, whatever. One typical thing you would do is you would engage some cloud service or something, right? Or maybe you can use like the supercomputer in your university or something like this. So what you would do there is you would upload the program and the input to this third-party service. They would run the program for you, and then they come back to you and say, here, this is the result of running your program on this input. It took me so much time, but this is the result. Right? And now you would like to be sure that what they're telling you is correct. Right? Because you're paying them money, you want to know what they're saying is correct, and they have an incentive to not be correct, right? Because this is a very expensive computation. So if they can save on resources that they are spending to do this, and just give you some answer, if anyway you cannot verify, anyway you cannot do the computation, if anyway you cannot verify it, and you would be none the wiser, then they have an incentive to do this. Like they may give you the wrong answer. Right? So you want to be sure that the answer they are giving you is correct. So you would like them to give you not just the result of the computation, but some kind of proof that this is in fact the result of this computation being run on this input. Right? And an important thing there is that the time it takes for you, the resources it takes for you to verify this proof they are giving you has to be less than the resources it would have taken you to compute the thing yourself. Otherwise, there's no point, right? So it has to be cheaper. And this is sort of a context, an example of a context in which this modeling makes sense, where you are the verifier who has fewer computational resources, and there is this prover, which is this big supercomputer, this service that has like many computers and so on, and they are trying to prove to you that something is true. So in that sense, their computational power is not unbounded, but it's a reasonable enough modeling that it makes sense to study, to model it this way, to model the prover as being computationally unbounded. In fact, you can actually get some upper bounds on the complexity, but we'll talk about that later if there is time.
So if we don't think of it this way, that the prover would brute force, then also is it correct to say that if we don't make the prover as all powerful, the system would sort of be would not be complete, because the prover could say that I can only find a proof of non-isomorphism between G0 and this particular instance only. I can't do it for a random thing that is sending me. So in that case, it would not be complete.
Yeah. So let me say it a different way. So if the prover had also been efficient, if you had placed the requirement, the prover is also efficient, it's also polynomial time, right? Then the entire system is polynomial time. There's nothing in the system that is not polynomial time. So you can do all of these things yourself. If you allow yourself to run in polynomial time, you can do everything that is being done here yourself if everybody here is polynomial time. Right? And that would give you an algorithm. Then if the system worked, that would also give you an algorithm, because you can just simulate the verifier and the prover yourself and see what happens. Right? So that also is a limitation of, if you said the prover is polynomial time as well, then there's this limitation that you will only be able to do this for statements that you can verify in polynomial time yourself anyway. Right? And this would be an issue with the completeness or soundness, like you said. So there are contexts in which maybe you do want to model it, do it that way, because one thing you can do even then, even if you ask the prover is in polynomial time, is you can say, okay, the prover is polynomial time, but the verifier is like a much smaller polynomial time than it takes. That would still be meaningful, and that would still actually capture, like the example I was giving you with like your laptop and like Amazon or whatever, right? That would still capture that setting, but it's just simpler to think of it as computationally onboarded. So let's stick with that for now. Okay, so going back to this, right? I have this proof system where I want the verifier to be polynomial time, but the prover's complexity I don't really care. So in that case, what we can do, as some of you are pointing out earlier, is the prover can now solve the graph isomorphism problem, right? It can take any two graphs and it will be able to tell whether they are isomorphic or not. So what the prover is going to do is, it has this graph, and it starts. Remember, the verifier is asking the prover to correctly identify which of these was permuted to get this, which of these was reliable to get the hedge, right? And the prover can now figure this out. It can take hedge. It can see, okay, G0 and H isomorphic. If so, then maybe the verifier, then that's what the verifier reliable to get this. And if not, then it must be G1. Then that's what the prover's algorithm is going to be. Simply going to say, if G0, and I'm going to just use this symbol for their isomorphic. Okay, it's just some shorthand. If these two are isomorphic, then the prover is going to respond with some bit indicating which of these it is guessing. So if these two are isomorphic, it's going to set it to be 0, and otherwise it's going to set it to be 1. Right, and then the verifier, after it receives this, it checks whether B is equal to B prime, and if they are equal, then it will accept this proof. It will say, okay, this is a valid proof, and it will accept it. And if it is not, it will reject this proof. This is the terminology I'm going to be using, that it either accepts or it rejects. Okay, and this is if and only if, but let me just make it more clear anyway. Alright, this is the proof system we are talking about. Right? And this proof system, you can verify that it has the two properties that we want. So if the two graphs are in fact not isomorphic, then the verifier will accept. Right? Why is that? Mm-hmm. Yes, on one observation that is perhaps implicit, so we're not thinking about it, but that is needed to complete this, to complete the argument for completeness, is that so if the two graphs are not isomorphic, then no graph can be isomorphic to both of them. Any graph will be isomorphic to at most one of them, right? Because isomorphism is a transitive property. So any H will only be isomorphic to one of them. So if it is not isomorphic to G0, it will be isomorphic to G1, and that will perfectly tell you what the bit B is. So that's why if the two graphs are not isomorphic, then the prover can always guess the B correctly. Right? And if the graphs are isomorphic, what can we say about this?
At most, it can guess randomly. Non-zero property, it will guess. H would be isomorphic to both of them.
Yes. So this is what we want to say. Good. This is a good observation. So let's look a little more deeply into this. So I wrote down this prover algorithm here, right? So what will this algorithm do if the graphs are isomorphic? It will always find that G0 is the same as is isomorphic to H. So it will always say it's 0, right? But then you can see that the bit B is 0 or 1 with probability half, but B prime is always 0. So it will accept with probability half and reject with probability half. Right. So, but that is this specific algorithm. What we would like, however, because remember the proof of soundness says that only true statements can be proven. But in this context, it's not sufficient to say that this particular prover algorithm cannot prove this statement. It's not sufficient to say that this particular prover protocol will not make the verifier accept with probability 1. What we would like to say instead is we would like to say that it doesn't matter what the prover tries to do. Because imagine the prover is, take the example we had from before, right, where this third party service is trying to convince you that the proof is correct, trying to convince you the statement is correct. So it's trying to make you believe, but what you have to say is that it doesn't matter what it tries, it should not be able to convince you. So you want to say it doesn't matter what algorithm the prover runs, it may be a different algorithm from this, it can do whatever it wants, it should not be able to prove that it's correct. For what we would like from the system. So let's talk about that now. So what would I like from the system? Again, I'm going to ask for these completeness and soundness properties, but let me start by just writing down what we discussed earlier, right? We would like the verifier to be, and I'm going to just use V for the verifier and P for the prover from now on. In the modeling of the system, we want the verifier to be a polynomial time algorithm, but we are not bounding the power of the prover. And now I'm going to write down, I'm going to take these two properties and I want to formalize them in this context, in this modeling of the system. Right? So the simpler property here is completeness. And here what I want to say for completeness is, so you have the system, if the graphs are isomorphic, then I would like the verifier to accept at the end of the protocol it should accept, that's what I want to say, okay. So I'm going to define this in the context of graph isomorphism first and then we'll generalize it to a broader class of statements. So here I want to say if the two are not isomorphic, then I want to think of this in terms of the probability the verifier will accept. Okay, rather than just saying it will accept or it will reject, because the whole thing is a probabilistic system, right? So it only makes sense to really talk about probabilities of events happening. So here I want to say that the probability that, and here is some notation I'm going to use, all right? So I'm going to use this notation to indicate that this is the result of the interactive proof when the verifier algorithm V is interacting with the prover algorithm P. Okay, think of this as the verifier's algorithm, this as the prover's algorithm. If these two sort of programs interact, this is the result. Okay, and on the probability that this accepts, I want it to be 1 in this case, and we showed that this is in fact true, right? Because if there's no way I can put this up there. Right, this is what I would like for in terms of completeness from the system. And what I want for soundness is going to be, and this is what I was trying to say. So I would like a stronger property for soundness. And I'll write this down and I'll again go over why we want the stronger property. Is so here, so this P and this V is specifically these algorithms, okay? So this is a specific prover algorithm that I have described here, and this V is a specific verifier algorithm written over here. Okay, and what I'm going to ask for the soundness property from this protocol is that I have this verifier V, right? This is the algorithm that you are running on your computer. You're not going to change that because you trust yourself, right? It's you are trying to verify something. But the person on the other side, the prover who is trying to prove something to you, they could be doing whatever they want. They may not be following this protocol, right? Because they have some incentive to prove to you that the statement is true, even if it is not true. Right? So you don't trust them. That's why you're even doing this. So if you trust this person completely, then you just take whatever they said to you and believe it. Right? But you don't trust them. That's why you even need a proof in this case. So they may not be running this particular algorithm. They may be doing something else. And what you would like is that it doesn't matter what they do. They should not be able to convince you of a statement that is not true. That's what we want. Okay. And to capture that, what I'm going to say is I'm going to say that for any G0 and G1 that are isomorphic, right? And for any possible prover algorithm that I will refer to as P star. Okay, this P star could be P, it could be other things, it could be anything. The only restriction is that it interacts in the format of the protocol. Like the protocol behaves this way, right? The first message is supposed to be like this graph that we call H. Second message is supposed to be a bit. So all this P star has to satisfy is that it has to fit the syntax. The types have to match of the messages, right? So and then you take any possible algorithm like this. I want to say that the probability that P star comma V. Okay, let me actually introduce a bit more notation. I'm going to write. So this is I'm describing the interaction of these two algorithms, and I'm going to write the inputs to the protocol. Let me do it here as well. So I'm going to write it as. It need not follow this algorithm, but it has to follow. Like it has to send a bit in response. It has to follow the type of messages. That has to match, because otherwise you will know, right? You are the verifier. If in response you're expecting a bit in response, instead if you get some number or some string, then you know that the prover is not following the protocol. So you can just say, okay, I don't believe you. So it has to follow the specifications of this protocol, but it may not be following the algorithm that you have prescribed the prover to follow. Right? Yeah, the verifier is following everything. Yeah, because the verifier is you. You are running it on your computer, so you have full control over what it does. And you want to know that the statement is true. So there's no reason for you to do anything else. Okay, so by this I just mean that these are the two algorithms involved in the protocol, the P star and the V, and they are given input G0, G1. Okay, so what I want to say is that probability that this accepts, I would like it to be something small. We'll be more specific about what later, but I just want it to be something very small. Yes. So what I want to say here is that if the the prover is trying to prove this a statement here, right? What is it trying to prove? It's trying to prove that the two graphs that we are dealing with are not isomorphic, right? The way it's trying to prove this is trying to show to you that it can actually distinguish between these two things. So what you would like out of this proof system. So imagine when we said here that all two statements can be proven, right? What does it mean for something to be proven? The way we are interpreting that in this situation is that the verifier at the end of the proof will accept. It will accept and say, okay, I have interacted with this prover, and I believe what it is saying. So that's what it means for the verifier to accept. It means that I have seen this proof and I believe this proof is true. Right? So if the statement is true, this is what the statement that the proof is claiming. If the statement is true, then you want the proof to succeed. Then you want the proof to be convincing. That's what we want, because that corresponds to this, right? It corresponds to saying all true statements can be proven. That's the same as saying if a statement is true, then the proof should be accepted by the verifier. That's equivalent to saying this, and that's what we are trying to say here. If the statement is true, then the proof should be accepted by the verifier. That's what completeness means. Whereas if the statement is not true, for any statement that is not true, right? And here also, let me write it in the same sort of language. So let me write it as for all G0 and G1 that are not isomorphic, and similarly for if the statement is not true, meaning that G0 and G1 are isomorphic, for any statement that is not true, for any G0 and G1 that are isomorphic, it doesn't matter what the prover tries to do. It doesn't matter how it participates in the protocol. It doesn't matter what it does on its side. It should not be, the proof should not be accepted. The verifier should not be convinced by the proof. Yeah.
For completeness also, shouldn't we have this for all prover algorithm some P? No matter what prover tries to do.
Mhm.
Like if it's a complete system, then this should hold still, right? This algorithm is that necessary. I can have another algorithm.
So it could be that there is some other algorithm that also has this property, but it's not necessary that every algorithm will have this property. For example, one possible prover algorithm is it will always send 0. Right? I can say the algorithm is b prime equals 0 and send b prime. Yeah, that's the thing. That's the point. That's if I say that for every p star this has to be 1 or it has to be large, then that cannot possibly be true. Yeah, you want to say that X is the prover algorithm, and in fact, as part of the protocol description, I am giving you the prover algorithm, and I want to say this: there may exist other prover algorithms also that have the same property. For example, if I put G1 here and 1 here and 0 here, that would also work. Right? So there could be other algorithms that also have this property, but I'm only asking about it for this algorithm. This is the same way as if you think of it in terms of mathematical proofs, right? For the same statement, there can be multiple different proofs. There can be different proofs that are all work, and that may be using different techniques, right? So, but all you want to know is that if a statement is true, there is at least one proof that works, and if a proof seems to be valid, then the statement it is proving should be true. These are the two things we want. Right? Yeah. Yeah, and that's in fact what we want now. This P star, I'm not bounding its computational resources at all. I'm saying it's an algorithm, but it can be, as you say, an unbounded Turing machine. It can do whatever it wants.
Why do we want the probability to be small? If it's less than 1, that is.
So ideally, in the end, what you want is you want very strong soundness. Right? Like if for example, if you have a proof system, where let's say that all you are able to do is get this to be like some 0.9999. So then what this would say, and we'll figure out how to deal with this later, but if all you had was this, then what would this be saying? This would be saying if there's a statement that is not true. Let's go to the previous example, right, where there is this computation you want to perform, and Amazon comes to you and says this statement is this is the computation, and then you run whatever proofs you run, and let's say this is the property it has, that if a statement is not true, that if it gave you the wrong answer, then the probability it will convince you is roughly 0.999 something, right? Now in this case it's not sufficient, right, because maybe in your entire lifetime you will run maybe 100 programs. So it's very likely that even if it returns a wrong answer every single time, you will never even see it. You will never see it. You will continue to believe whatever it's giving you, but it will never show up that it's actually. But everything it's giving you is wrong. So the proof is not very useful. So that's why you would like this to be very, very small. You would like this to be as small as it can be. But the nice thing is that you can actually make these things smaller in general. I will get to that in a minute, but are there any other questions until this point? Anything that's not clear so far? Right. So, and so in this case, what can I actually put here? So in this particular protocol, what do we actually have? If I run this protocol once, what is the, so in this case, the probability is in fact 1, right? It is actually 1. But in this case, if the graphs are isomorphic, what is the probability that this protocol will accept? What bound can I put here? Half, right? I can say that it's always going to be, in reality, it's always going to be less than a half. And actually, it's you can actually even say it's equal to a half, because because they're the same thing, right? And they're independent. So in this case, usually often you'll only be able to get upper bounds, but in this particular case, you can actually say it's going to be equal to a half. But you would like this to be smaller. Half is still not that satisfactory. You would like this to be very small. So what would you do? How can you make this smaller? Yeah, you just repeat it many times and it becomes smaller. So it's a very simple thing to do, but it's not. It turns out in general, it's not that easy to prove. Even in this case, actually, it's not that easy to. Actually, in this case, maybe it's simpler to prove, but in general, you can do this with any kind of a interactive proof system like this. You can make the errors smaller by repeating, and we'll see that in a minute. But it's a little non-trivial. But before I get that, I want to think about this more generally. So we have seen an example of an interactive proof system. We have seen the properties that this proof system had. But now I want to abstract this out. I want to think about more general kinds of statements and write down what I would like from proof systems that prove slightly more general kinds of statements. Okay, and the way I'm going to formalize this, the way I'm going to define the properties I want from a proof system, is going to be in terms of what I will refer to as promise problems. Have people encountered this term before? How about languages? Have people encountered the term language? How many of you have heard of languages? Okay, so let me describe more. Let me define these things anyway, so that we are all on the same page. And I'm going to be talking in terms of what are called promise problems. Okay, which is a sort of generalization of languages. You'll see what I mean. And I'll explain why it's called a promise problem in a minute as well. And it's nothing too sophisticated, okay? Like a promise problem is simply a pair of sets, a pair of disjoint sets. Alright? So a promise problem, and I will typically use the term pi, use the symbol pi to refer to these things, just like you use L for languages, suppose. And all it is a pair of sets, alright, such that these and what the property that these sets have is that they are for now they don't have to be this way, but typically we will think of them as strings, because you can represent anything you want as a string, right? So it's not a big deal, and I want the intersection to be empty, right? And I'm using the symbols y and n because these are sometimes called yes instances and no instances. Okay, yes and no basically meaning that things in the yes instance, I will typically say they are in the language or in the problem. A no instance will be like it's not in the language or not in the problem, right? So it's if this y and n if the union were equal to 0, 1 star, that's what you typically think of as a language. Right? With a language, you have like one set, and you're asking is a string in the set or not in the set. Here I have two sets that may not cover the entire space. There may be strings that are in neither of these sets, but I don't care about those strings. If some string x is not in y and not in n, then I don't care what you do with that. I'm promising you, that's why it's called a promise problem. I promise you that whenever I ask you to solve this problem, whatever string x I give you and ask you to solve this problem on, it will lie in either y or n. That's the promise I'm making. And then I ask, okay, is it in y or n? That's the question you're asking. As an example, in this case, right, for the graph non-isomorphism problem, let's say I write it as G and N. This is the symbol I'm going to use for the graph non-isomorphism problem, and this consists of some y and n. So I'm just writing this So it just says YGNI and NGNI. Yes, and here this is simply, what is the set Y here? I see. Okay, then I'll have to bring it all the way down. So it's because it's not visible over there. I see. Okay, is this visible to everybody? If I write here, can you guys see? Okay. Yeah. So if I want to sort of frame the graph non-isomorphism problem in this kind of a language, what would this be? What would the set Y be for this problem? Yeah, exactly. So this is going to be a set of graphs G0 and G1 such that they are not isomorphic, right? And similarly, the no set is going to be the set of G1 that are isomorphic, right? And the promise sort of in this case is that because I sort of set it up as strings, right? I set this up as the elements of these are supposed to be like strings, but depending on how you encode your graphs, not every string may represent a legal graph. Maybe a valid representation of a graph, and that's the promise I'm making to you. The promise is that I will give you a string, and it will represent a graph in whatever representation of graphs you're using. So that's the promise. But apart from that, these are the yes and no instances of this problem. Okay? So I'm going to give you some string really because these are supposed to be like sets of strings, right, of length and of some length. Now, how do you represent a graph? There are many ways to represent graphs. You can represent it using the adjacency matrix or some adjacency list or something. But it could be that let's take an example, right? Let's say you represent a graph using an adjacency matrix, meaning that if you want to represent an n vertex graph, then what will be the size of its adjacency matrix? N squared, but how many bits will you need to represent it? So actually you'll only need, let's say it's a full adjacency matrix, right? Because the matrix is symmetric and also the diagonal is always doesn't matter because it's a simple graph, let's say, there are no self loops or whatever. You only need n choose 2 vertices bits to represent it because you take every possible edge and you're asking is this edge there or not. That's the bit, right? So you only need n times n minus 1 over 2 bits to represent a graph of length n, graph of n vertices, right? Now, if I give you a string that is of this length, then you can interpret it as an adjacency matrix of some graph. It will define some graph, right? But if I give you a string that is of length that is not of this form, because only few numbers of this form, right? If I give you a string of length 3, which is not like this, then it will not represent any graph. So that would not be a valid instance of this problem. That's what I would say. That is a string that does not satisfy the promise. The promise I'm making in this case is that I will only ask you to solve the GNI problem on strings that actually represent graphs, actually represent pairs of graphs in this case. And that's the promise. And beyond the promise, so usually the promise is not something you really have to worry about because it's usually a lower level detail. Not always, but in the examples that we are going to see, it's going to usually be a lower level detail. So typically don't have to think of the promise, but this is the promise in this case. There could be two reasons why you need a promise. One could be simple lower level representation reasons like this, but there could also be like higher level reasons. There could actually be meaningful reasons why you want to think about promises. For example, maybe I want to think about a restriction of this problem, right? Where I say either the graphs are actually isomorphic or maybe they are far from being isomorphic. That even if you change a few of the edges, they don't become isomorphic. That could be like a restricted version of this problem, of the graph non-isomorphism problem. So in that case, I will redefine my promise to say I will only give you graphs that are either the same or are actually very different. Not only are they not isomorphic, they are quite far from being isomorphic. So I can think about examples like that, and in some cases it makes sense to think about stronger promises like that. But for today, it's not really going to matter. Okay. So is the formalism okay? This is what I mean by a promise problem. And whenever I talk about interactive proofs for the rest of today, I'm going to talk about interactive proofs for some promise problem. And by this I mean that this is a way for me to interpret these two conditions, right? So whenever I want to talk about interactive proof, I will first say we are only talking about this one particular promise problem, and then the true statements for the problem will correspond to the set to the elements in Y, right? And false statements will be the elements in N. So here I should really restate this a little bit. Instead of saying all only true statements can be proven, I want to say it differently. I want to say no false statements can be proven, because there are statements that are neither true nor false, which are the statements that are not in the promise, right? So I want to restate this, and instead of saying this, I want to say right, and false statements are basically the whatever is in N, and true statements are whatever in Y. So I'm not going to use this. I'm going to use this interpretation of soundness. Okay. So in that respect, now we are in a position to define what we want, to write down what we want from an interactive proof in the context of some particular promise problem. Okay, and so we are going to say, and an interactive proof is specified by these two algorithms, by some algorithm P and some algorithm V, and that interact in this protocol, right? They have to be compatible in that they expect to receive the same messages and send the same messages and so on. But an interactive proof, which is specified by proof system, which is specified by these two algorithms, I will say is an interactive proof, and I'll abbreviate it as IP. It's just interactive proof for a promise problem pi, if it satisfies the completeness and soundness properties defined with respect to this. And this, the modeling that the P is unbounded and V is polynomial time is going to be there throughout. Okay, so I'm not going to explicitly mention it every time, but this P is computationally unbounded, and the verifier has to be efficient. On top of that, the properties you want are completeness and soundness, basically. So for completeness, you ask that it's going to be exactly the same as over here. So here we said for every statement that is true, the verifier has to accept, right? So I'm going to say for every statement that is some string X or in this case like a pair of graphs, for every object in the yes set, if you run the actual algorithm as specified by the protocol itself, then the verifier should accept this proof. Right? So for this, I'm going to say the probability that if you run this P and this V with input X, the probability that it accepts is, for now I'm going to write this is large. We'll figure out exactly what to put here in a minute. And soundness is again going to be a straightforward adaptation of that. Here I want to say for any instance, and that's what I'll be referring to these things as instances. Okay, they're just strings with their instances. For any instance that is, for any no instance, it doesn't matter what algorithm P star you use in place of the P, the probability that P star V when given X, the probability that this accepts has to be small. Okay, and this is going to be my definition of an interactive proof for a promise problem. Pi. Yes. So the way it's going to work is there is some promise problem, and then I come up with one specific protocol like I did over here. Like here I specified what the algorithm for the verifier is going to be, what the algorithm for the prover is going to be. I come up with this, and then I tell you this is an interactive proof system for this particular problem, this particular language, this particular promise problem. What does that mean? This is what it means. it's supposed, the system that I present to you is supposed to satisfy these two properties for it to be considered a valid interactive proof system for this language, for this problem. These are the requirements I place on this. Right? And now, so now what should this large and this small be? Over here, we were able to get, if you run this just once, we got like 1.5 here. And we had observed that if you repeat this, you can improve this. You can make this like, if you repeat it like t times, this will become like 1 over 2 to the t or something like that. Because you will check that every single time it is correct, right? So this should go down exponentially. So I can actually make this quite small. And in fact, you can do this more generally as well. So what I'm going to do here is, instead of I'm going to start by writing down what I would really like. So I would like this to be something that is very close to 1. Right? And for now, let me just say 1 minus something that is little o of 1. I would like it to be very close to 1. And here I would like this to be very close to 0. So I would like it to be something that's little o of 1. Right? But fortunately, it turns out that the approach we had to amplifying the soundness condition in this case, by we just repeated this many times and checked that all of them accept, right? It turns out that you can actually do it for general interactive proofs as well. You can take any interactive proof, let's say, that has, for example, here, let's say you start with something that is 2/3 here and 1/3 here. Right? You have an interactive proof where the only promise you have to start with is that in this case, for yes instances, it accepts with probability 2/3, and for no instances, it accepts with probability at most 1/3. Then it turns out you can actually transform it. You can go from, there is some transformation you can do that will both increase the probability in this case and decrease the probability in this case. Right? One simple example of this is if you had started with perfect completeness, by which I mean if you had started with something that is 1 over here and half over here, as in the example that we saw, then it's quite simple, right? You can just repeat the protocol many times and you make sure it accepts every single time. Right? What would you do in the other case? Let's say, and that actually works. We'll see in a minute how to prove that it works, because it's not fully trivial to prove that it works. But so in this case, when you start with perfect completeness, then you just repeat many times and you make sure every single iteration of the protocol accepts. Right? But what would you do in this case? Let's say that I gave you some interactive proof system that had completeness 2/3 and soundness 1/3, right? Where I said, if yes instances you accept with 2/3, no instances you accept with 1/3. How can you go from how can you change that in a way to get a different system that gets 1 minus little o of 1 and little o of 1 here? What could you do? So you repeat, and then what do you do? Yeah, so this is the kind of thing we're going to do. So imagine, again, you take this proof system and you repeat this t times, right? So if everything was really nice, then you would expect that if you are working with an instance that's a yes instance, every run of this proof system is supposed to accept with probability more than 2/3. So we'd expect that if you run it t times, then on about 2/3 of the iterations it would accept. Right? And similarly, if you have a no instance, if you one iteration accepts with probability at most 1/3, so you would expect that at most t over 3 of the instances accept. Right? Of course, it's not going to be always like that, right? Because there's randomness here. There's even in this case, there's a small probability that all of your instances will accept. But the idea is it's very small, and that's why you have this little o of 1. You can show that if you run it enough times, then with very high probability, fewer than half of the runs will accept in this case, and more than half the runs will accept in this case. So all you have to do is repeat it many times and check whether a majority of the executions are accepting. And that will give you, in fact, that will actually give you something even stronger than this. You will get some kind of exponential improvement. So you can go from here to something that's exponentially small in t, and you can go from here to something that is 1 minus exponentially small in t. Right? So you can in fact get something that is not just little o of 1. Let me write it here. So if your so you have your completeness and soundness probabilities, completeness and soundness parameters. If you have a single iteration, if you start with any constant that's larger than, you can do this with really, as long as you have any sort of separation between these two, you can do this, right? But as an example here, if you start with 2/3 and 1/3, and if you do t iterations of this, you can actually get something that is 1 minus, and this is like exponentially e to the minus theta of t. Like there is some constant such that you can get 1 minus e to the minus that constant times t. And similarly, so this is greater than, this is less than, this is similarly, this probability you will accept in this case also goes down exponentially. So you just have to repeat and take the majority. T iterations. Okay, that's how you amplify these proof systems. Yeah, it's minus e to the power minus theta of t. Good. Thanks for asking. Let's see how you can get this. So let's start with the simpler case. Actually, let's start with the case where you have, let's say you start with 1 over here. In which case you can actually expect this to be 1. But let's start with 1 there. Let's even start with a simpler approach, right? If you have perfect completeness, then you know that you can do something simpler. So if you have 1 over here, then you don't even need to take the majority. You can just ask that every single iteration passes. Right? So I start with an interactive proof. So I'm going to write this. I'm going to describe this new interactive proof system, which I'm going to define as, which I'm going to write as, I will call it p to the t and v to the t. Okay, I'm not actually doing any arithmetic operation here. This is just my notation. So I'm going to define this using a proof system PV. Okay, and what this is going to do is it just you just repeat p comma v t times, and you accept if and only if all of them accept. Right? So what I'm trying to do is I'm trying to do this kind of transformation, this kind of amplification in the case where you have perfect completeness, in the case where you have in the yes instances you accept the probability 1. Because it's a simpler situation, I want to start with that. We'll talk about what you do in the more general case later. I mean, we know what you do, but we'll talk about analyzing it later. But I want to take the simpler case and analyze what happens over here. Right? And this is exactly what we did with the examples so far. We just repeat many times and make sure all of them accept. Right? And now here, what do I want to do here? I start with a p comma v that satisfies both these properties with 1 over here and let's say a half over here. It doesn't matter what constant it is. And I want to get a pt vt that has like still has like 1 over here and something very small over here. Right? So I have to prove that. So let's prove that one by one. Right? First, I want to prove the completeness condition for this. So here, so for completeness, I want to prove that. I want to talk about what is the probability that so we take some yes instance of the language, and we are asking what is the probability it accepts. So what is the probability it accepts, and why is it 1? Right? Yeah. So it will accept if and only if all of them accept, and all of them are going to accept because the original proof system had the property. So this is going to be 1. Right? But the harder thing to argue is the soundness condition. Okay, let me think about what I want to remove. I'm going to erase this, okay? Yes, so here so it takes some instance that is no instance, and now I want to understand what is the probability, and I want to upper bound this probability. I want to upper bound this. Okay, it takes x as input. I keep forgetting to write that. It takes x as input, and I want to upper bound the probability it accepts. And the only thing I have to start with is that if you take actually it's more than that, right? It's not just this particular PT, because I want to prove soundness against any possible prover, right? But let's start with this. So let's say I start with just the PT and VT. So then what can you say? What is the probability that if the prover actually behaves the way it's supposed to behave? What can you say about this? So we are starting with this being less than 1 by 3. So we don't know exactly what the number is, but you know it's less than 1 by 3. So this is less than 1 by 3 to the power t, right? And why is it less than 1 by 3 to the power t? It has to accept on each of the iterations for it to accept, right? And an important thing to note here that is sort of going unsaid, but that we are thinking of intuitively, is the fact that all of these iterations are independent. Right? This is very important, because all you know is that every single iteration accepts a probability at most 1/3. But because the prover is running the actual algorithm, because it's actually the prover is also running the P algorithm independently every single time, the entire iteration is independent. So the entire first iteration is independent of whether the protocol accepts in the first iteration is completely independent of whether it accepts in the second iteration, because you're starting anew. Both the prover and the verifier are running P and the V, and they're running it independently in each case, right? So that is important. Yeah.
This like 1 by 3 statement, they're using P star. Why did we choose not to use P star for that?
Yeah, that's what I want to do eventually. I wanted to start with a simple case. If the prover was actually running with this PT, then you can do this, right? But can you do this? So what do I really want? I want to say that for any P star that you could be using, can you say the same thing? I want to bound this, right? Probability that the verifier is still the same, because the verifier follows the algorithm that was specified. So it's going to run T times, assuming that on its side it's going to do things independently, right? So, and this is what I really want to bound. This is what I want to bound, right? Because this is this for all P star is part of the definition, right? And now this is a bit more tricky, because now we no longer have this independence. Because the verifier is acting independently in each iteration, that you know, but what the prover is doing, you don't know. Like it may be sort of acting in some correlated manner across the first 2 iterations, for example. It could, for example, say something like, okay, if the first iteration rejects, then I'll do something in the second iteration. If it accepts, I'll do something else in the second iteration. You don't know what it does. That's the problem, right? You want to be able to make this statement about every possible algorithm, and you do not know what the algorithm is, and that makes it much harder to argue that this is happening.
So then we need to show that this prover, which sort of learns as it goes,
Mhm.
it can be replaced by a malicious prover of sort of which I mean this thing. It can be replaced by a prover which would sort of not learn. I mean,
Yeah, this is what we would like to do. And this is actually one way of doing what we want to do. So let me repeat this. We would like to say, okay, in general, we have no guarantees about independence across the different iterations, right? Like we don't know what the prover is doing. But what we would like to be able to say is that, okay, whatever the prover is, there is some prover P star that's doing something. What all we really care about is the probability it accepts in all the iterations, right? That's all we want to model. So what we are going to do, what we can try to do is we can say, okay, this prover, this P star is acting in some, maybe acting in some arbitrarily correlated manner across the iterations. But what if I can construct a different prover that has whose acceptance probability, such that the probability that you accept when interacting with this new prover I am constructing is at least as much as this. So it's more than this, it's greater than or equal to this, but it does act independently. Right? Yeah.
Like, why can't we in this scenario? Because we know verifier is doing a prescribed thing only. Given we also know in this case, assuming all the instances come from the no set only, then why can't we just analyze it from the verifier's perspective? Like, is it wrong to say that whatever algorithm the prover uses, if that is from no instance, the verifier at the max can get b prime equal to b half the time. So why is it wrong to just bound it by 1 by 2 to the power of t, something like that?
So so the statement is true. So it's hard for me to give a counterexample for this, but the way we want to prove it is, so let me show, okay, let me start with this actually. Let me start with the natural approach to proving this and let's see what goes wrong with that, right? That will be a more concrete thing for me to say than to just talk about these correlations. And then we can come back to actually proving this, right? So here is, okay, so I have t iterations of the protocol, right? So this is what the entire thing looks like. There's pt and there's vt, and there's some x that they are trying to do the protocol for, and they're supposed to be doing t independent instances of the protocol, right? These are like, they're supposed to be t independent instances of the protocol, and vt is actually acting independently in all of them. But the concern is this p star, now it's some p star, right? It may not be this pt. It may be doing some weird things in between. So how do I talk about this? Well, here is one natural way to argue about the probability that all of these things accept. Okay, I would like to define events that capture the acceptance in each of this iteration. So I'm going to define for I from 1 to t, I'm going to define an event. Okay, this ei, it indicates whether in the ith iteration the verifier accepted. So in each of these cases, the vt is running some v, right? And this v is independent in each of these. But on this side, you don't know what the prover may be running some correlated algorithm. You don't know what it's doing, but you know the verifier is independent in each of these things, right? So I'm going to define this event ei, which is that the in the ith iteration, the v accepts. Fix some x. Okay, we can argue this for every single x. So just fix the x and forget about it for now. So I'm going to define this event. Right? In the ith iteration, the verifier accepts. And now I care about this, right? I care about the vt is defined to accept if and only if all of the iterations the verifier accepts, right? So what is the probability I care about? Like this probability, how do I write it in terms of the EIs? It will be the intersection, right? All of the events have to happen. The E1, E2, all of them have to happen, right? So this is just E1 and E2 and ET, right? Now, this is simply by the Bayes theorem. This is simply the probability that E1 happens times the probability that E2 happens given E1 happens, and you just take the product all the way until you get to probability that ET happens given that E1 happens and all the way up to ET minus 1 happens. Right? This is what this probability is equal to. Right? And now, okay, now what can we say about these things? What can we say about these each of these probabilities? They're all less than 1, but we want something more because all probabilities are. Oh, you mean strictly less than 1? Yes, about in this iteration, does the verifier accept? In this iteration, does it accept? So let me give an example. 1 second. So let me give an example for why that may not be the case. Right. For example, what I could do is, let's say I am this P star, right? I am interacting with the verifier in the first iteration. So with some probability it accepts, with some probability it rejects. Let's say what I do is I say, okay, if in the first iteration the verifier accepts, then in the second iteration I will make the verifier reject, because it's easy to make the verifier reject, right? I can always send the wrong answer or refuse to interact. So I can change the value. So in that case, the probability of E1, let's say in the first iteration I act exactly the way the P is supposed to act, right? So in that case, it's fine. The probability verifier accepts is the probability of E1, you know, is the probability that V accepts when interacting with P. But in the second iteration, in this thing, I can change this. So if the E1 happens, if the verifier accepted in the first iteration, I can look at that and I can make the verifier never accept. I can make this 0. And things like this I can do. So it may not be equal. So because of this, there is no independence. So you can't say this is equal to the probability that E2 happens. Yeah.
So we can show that individually each of them will be less than 1/3. As suppose it's a machine acting in the event. So let's say it has an internal state which is something dependent on previous events, but it is something. And it is fixed at the start of the event, and now the protocol happens and it outputs answer. So now let's say if the probability of this event accepting was greater than 1/3, that state, if we had kept this prover for single event case with that starting state, then that probability would have been greater than 1/3, which rejects the initial soundness assumption for one single, because for every P star it had probability less than 1/3.
Yeah, this is pretty much how we are going to complete this proof. Okay, so let me repeat that, but before I go there, let me point out what is happening here. So, and how it squares with the example I just gave, right? What did I just say? I said that this may not be equal to the probability that E2. So you know that what you know is that for every I, the probability that EI happens is at most 1/3, right? Because if it is not the case, and this is what we want to argue right now. But what the example I gave just now was, I said that this you can change and make it not be equal to E2, the probability E2 happens, but you can only decrease it. You can't increase it. That's the observation. That's where we want to get. Right? The thing is, you cannot increase the probability that E2 happens given E1. It cannot be more than the probability that E2 happens, right? Because that is going to contradict the soundness. So to make this more precise, let me just repeat what you were saying right here, right? So I want to argue something a bit different. I want to argue that for any I, a probability that EI happens, given that all the previous things have happened. This is like each term in this product, right? I want to argue that each term in this product has to be less than 1/3, because suppose it is not. Suppose E2, suppose the second term, probability E2 given E1. Okay, let's start with the beginning actually. If the probability even happens is more than 1/3, that's a contradiction to soundness, right? Because when I can construct a prover for the base protocol that I started with, that just runs like the first iteration of this protocol and interacts with the verifier and makes the verifier accept with probability more than 1/3. Right? So clearly for E1 this has to be true. If I equals 1, this has to be true. Now suppose it is let's take I equals 2. right? Suppose for I equals 2 you have, suppose this term is larger than 1/3. Suppose this is larger than 1/3. Then what you can do is, what does this mean? What this means is that if in this iteration, so there is an instance x that's fixed. If in this iteration the verifier accepts, that means even happens. If it accepts, then conditioned on that, we are saying the probability that the verifier accepts in this iteration is more than 1/3. Right? And now we are going to use that to construct another prover for the base protocol that makes the verifier accept with more than 1/3 and breaks soundness. Right? And the way you do it is, okay, you know that conditioned on accepting here, the verifier accepts here with high probability. Right? So how can you emulate this conditioning? Well, the prover is computationally unbounded, right? It can do whatever it wants. So imagine a prover that does the following. So it starts running. So this is a prover for the base protocol, for just the P and the V. I'm constructing a protocol for the single iteration. But what it does is, at the beginning, it runs one iteration of this protocol and keeps running it until it finds an iteration which accepts. Right? And it can do whatever it wants because it has unbounded time. So it keeps simulating this part. So the prover simulates this part of this protocol on its own and does it until it finds a run which accepts. And then it maintains some state. So the prover, this P star, it keeps going down this here, right? And it keeps maintaining some state over here. So this prover that I'm constructing now is going to just run this until it accepts and then just keep running it. But now it is going to actually interact with the actual verifier. And now you know that the probability that the verifier accepts the second time, given it accepts the first time, is larger. So that would give you a contradiction. That will give you a prover that can act in the original protocol and succeed with probability larger than 1/3. And this is a contradiction. Yes. So I'm going to repeat this over. I'm going to erase. I'm going to erase something over there. Yes. Yeah, it is sort of because the prover can simulate the verifier. So what I'm going to do is, I'm going to prove this one statement, but it's more general. You can extend this to other i's as well. Suppose this probability is greater than 1/3. Okay, suppose this probability is greater than 1/3. Now from here I want to construct some, let me call it P hat. Okay, I want to construct a different bad prover for the base protocol. I want to construct some P hat such that the probability that when interacting with P hat, the verifier, the base verifier, the verifier for one iteration, right? Verifier for the base protocol, the probability that this accepts is more than 1/3. Right? This would be a contradiction to soundness if I can do this. If I can construct such a P hat, that would contradict the soundness of the protocol I started with. So it cannot exist, which means this has to be less than 1/3. That's what I want to do. Right? So how am I going to construct this P hat? What do I have? I have this P star. Right? I have this P star. Basically, this P star which gives you this property. Right? This is the same as saying that this is the probability that like the second iteration accepts, given that the first iteration accepts. So given the first accepts is more than 1/3. Right? And I want to use that to construct this P hat. So what am I going to do? How am I going to construct this P hat? Let me write down the entire algorithm for this P hat. So p hat, it's given some input x and it's interacting with the verifier v, which also has the input x, right? So I want to describe what p hat does in this case. So what p hat will do is this p hat it's going to simulate an interaction, the first iteration in this interaction. So if when p star interacts with this vt, it has t iterations, right? But what p hat is going to do is it's going to run just the first iteration, and then it runs the first iteration and just sees did the iteration accept. If it did not, it's going to repeat it, right? So it's going to start over. So it's going to keep repeating this iteration. And because it is simulating everything, it's simulating the verifier on its own inside its head, it knows whether it would accept or not. So it repeatedly simulates the first iteration. So it starts from the beginning, it runs the first iteration. If it accepts, it's going to do something. If it doesn't accept, it starts over and it keeps doing this. And it has an unlimited amount of time, right? So even if the probability that the first iteration accepts is very, very small, it can run until it finds it, until that happens. Right? Unless it's 0, which is some weird case. Let's not talk about that. So it can keep doing that until it accepts, right? And once it does find an iteration, then it's going to continue running p star, but now it's going to interact with the actual verifier, right? Once it finds this thing, and it's going to continue to the second iteration. But now it is not going to simulate the verifier itself. So in this case, until here it was simulating the entire verifier, right? It was simulating the verifier as well, but now it is going to interact with the actual verifier. Right, so in some sense what's going on is p hat is here, the v is here. In the beginning, p hat inside its head, it starts the interaction between p hat and the first iteration is just one v, right? The first iteration is just v as well. So it interacts with this, and then once it finds an accepting interaction, it continues running this. It continues running this p star, and now it interacts with the actual verifier. So it keeps doing this until it finds an accepting instance, an accepting iteration, and then it continues running this. And now you have achieved the condition that you wanted. Because you ran this until it accepted, you have achieved the conditioning that the first iteration accepts. Right? That's why you did this. You wanted to condition on that. You wanted to condition on the world being in that situation, the world being in that state. And now by repeating this until you found an accepting iteration, you have set things up so that the world looks like the first iteration is accepted. And now you continue talking to the actual verifier, the world looks exactly like the second iteration. So the probability that the verifier accepts in this case is exactly the probability that the second iteration accepted given the first iteration accepted. Right? So the probability that this whole thing accepts. So probability that p star comma v accepts, and again I'm ignoring the x everywhere, is going to be exactly the probability that probability of E2 given you, which is greater than 1/3, and this is a contradiction. And then you can do this for all the other iterations as well, and this will prove to you that each of these conditional probabilities is less than 1/3, meaning that this entire product is at most 1/3 to the t. So this will say, I don't have space to write it, but is that okay? Oh yeah. I think we are way overdue for the break. So let's take. Are there any questions? Yeah.
Starting you said that this is a correct you said this is a wrong.
So the wrong proof would have been to say that all of these are less than 1/3 without thinking about the independence. So you have to think about the statement is true, and it's also true that each of these is less than 1/3, but the proof is not that straightforward. That's what I wanted to say. Okay, so let's break for half an hour. Yeah, let's break for half an hour, and we'll have a shorter session after this, and then we go for that.